Okay, hello Discrete Math. We're recording a quick video about Eulerian circuits, and this is something this is a core theorem of graph theory, and it's actually something that we started covering at the very end of period 8 on Friday, but we didn't do it in period 9. And actually this is begins this conversation usually with a story about a city called Koningsberg, and Koningsberg is this is the sort of Germanic name for the city. It is now called Kaliningrad. I believe that's still true. I think that's true. And this was the capital of Prussia, and it is now the state of Kaliningrad, which is that little piece of Russia which is on the Baltic that's not contiguous with the rest of Russia. So it's like on the other side of Lithuania, I want to say, borders Lithuania and Poland, something like that. Anyway, this city, Koningsberg, one of these kind of old north central European cities, and Euler, who is basically the person who single-handedly invents modern graph theory, it all comes down to this particular problem. And this particular problem says, okay, we have this city, right? And here is one part of the city. So this is over here, this is like land. And over here, this is also land. But we have a river flowing through the city. So there's sort of water here. So this is all water. And I think this is roughly an accurate picture of the situation. Water, 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 water. This is all water. And then we have these bridges. So this island A, this is what this is. This is kind of a small island in the center of the river. And this point D is kind of a peninsula. And the river meets, the river sort of splits on either side of this peninsula. Okay, so if you've ever been to Europe or lived in Europe, it's very cute. All of the cities of Europe, grew organically over a period of hundreds and thousands of years. And so there's always a big, gorgeous, beautiful river flowing through the center of every city, and that's sometimes true in America, but sometimes we just have big dumb cities in the middle of nowhere, just because, like Las Vegas or something like that. But anyway, here we have this beautiful river, and there are these bridges. Okay, so here's a bridge. What is this bridge? It connects the mainland over here. Let's just call this the south bank of the river. I'm not sure if that's right, but let's suppose it is, to this island. And there's another bridge also connecting the south part of the city, the mainland, the south bank, to this island A. And then there are two bridges connecting this island to the north bank of the river, the mainland over here. Then there is a bridge connecting the mainland to this peninsula, and another bridge connecting this mainland to the peninsula over here. And then finally, there is a bridge over this little bit of water connecting the peninsula to the island. All right. So there are 7 bridges in this city, and this is called the Bridges of Koningsberg problem. And the question goes something like this. If you are out for some kind of evening stroll through the city, perhaps you want to take a walk around in a big circuit. Okay, so what's a circuit? You start somewhere at your house, say, and you walk in a big loop all the way through the city and back home again. And the idea is, let's cross every bridge. Okay, well, you can certainly do that because there's only 7 of them. So if you walk long enough, you can certainly cross every one. But it's kind of annoying or maybe inelegant or something like that to cross over some bridge twice. So now the question becomes, is it possible to find a circuit in which you cross every bridge exactly once? So you can imagine this sort of thing, or perhaps you want to have a military parade which parades exactly once over each of the 7 bridges. And if you try to do this problem, you will certainly find that it's really hard, say you want to start here, down here. Let's see. If you want to start down here on the mainland, then well, if you cross a bridge, so now you're in the island A. Well, if you cross a bridge again, you got to leave somehow. So I don't know. Maybe you want to go to D. Well, if you go to D, then maybe you want to go, I don't know, arbitrarily back. And now, maybe, well, now you're stuck because you've used this bridge and this bridge, so there's only this one left, so you sort of have to go to Island A. And, well, you can't go to D because you already used that one, so you need to go north. And now you're up here on the mainland, and now you realize, oh, man, there are two bridges left. There's this one and this one. If I go down to the island, I'm stuck. There's no way to leave ever again. And if I go to down following this bridge to the peninsula, then there's no way to ever get back to the mainland to ever use this final bridge. And okay, you can try this over and over and over again, and after 2 minutes or something, or 5 minutes, or 10 seconds, you can convince yourself that there's just no way to do this. This is a kind of a classic kind of discrete problem, and though there was, very sophisticated mathematics at this time, including calculus and everything like that, no one had ever really stopped to try to develop a theory that would enable one to prove something like this. So Euler, a mathematician, says, okay, I would like to prove this fact. How can we, in fact, give a rigorous proof that there is no such way to use every bridge exactly once? And what Euler does is essentially invent modern graph theory. And the argument goes something like this. He says, okay, well, look, all that matters when I cross a bridge is where it connects me to. Once I'm on, say, the island A, I'm free to move about the island however I want. That doesn't affect the mathematics of the situation. So you might as well consider the entire island to be like a point. And you might as well consider the entire north bank of the river to be a point. Because once I'm on the north bank of the river, I'm just on the north bank of the river. And when I cross a bridge, what I'm really doing is connecting myself from this island point to this north bank of the river point. And similarly, we can create a point down here in the south bank and a point here on the peninsula. And every time I use a bridge, what I'm really doing is going from one sort of point to another. And now, what we've done is we've taken this geometry problem involving the layout of a city, in which there are sort of potentially, you might say, an infinite number of paths through the city, and we've abstracted away from the particular geometry of the situation to now a discrete problem. And the discrete problem, which, okay, we've been doing graph theory now for like a week, so this should strike you as maybe obvious that what we now have is a graph. And the vertices of the graph are the 4 regions of the city, and you can only move from one region to another by crossing a bridge. And so the vertices are the regions and the edges are the bridges. And now we have a problem which is amenable to mathematical analysis, and that is, does there exist a circuit or perhaps even just a trail? The idea is we want to use every edge only once. So is there some walk through this graph which uses every edge exactly once? That's called a trail. And not only, well, okay, that uses every edge only once is a trail, but that uses every edge. And so this is called an Eulerian, or some people say this Euler trail. An Eulerian trail is a trail. What's a trail again? It's a walk that does not reuse edges, and it's an Eulerian trail if it also uses every edge. So uses edges at most once, but also at least once. So it uses every edge exactly once. That's an Eulerian trail, and an Eulerian circuit is one that starts and ends at the same place. So you might even ask, is there a walk through this? Is there an Eulerian trail through this graph? A walk that uses every edge exactly once, but now I'm not even demanding that I start and end at the same place. And I think the answer is still no, right? Our argument from before showed that. All right, what is the property? So I think the key brilliant move here is the abstraction away from the geometry of the problem to the discrete problem of vertices and edges. So this is what Euler did, and now I think it's a pretty simple argument that no trail exists, because this vertex has degree 3, this vertex has degree 3, this vertex has degree 3, and this vertex has degree. Once again, when I point with my stylus, no one can see the mouse move. It's very distracting. So I'll just do this now. So this has degree 5, degree 3, degree 3, and degree 3. Yeah, so the claim is that this can't be done, because as I move along the edges, I go sort of one in, one out, and that's always going to reduce the degree of the vertex by 2. And so if you have a vertex of odd degree, then I'm going to get stuck. Okay, that's the entire proof. I'm extremely tempted to just not even make this video and just tell you, hey, read the book, because this is such a famous and basic core part of graph theory. In like every single graph theory class in all of the world, they do this proof. And so it's pretty arrogant of me to think that my presentation will be any better than what's already out there. However, I don't like any of the presentations that are out there. And so while you could just stop watching right now and read the textbook, I don't like what the textbook does so much. And so what I've done is maybe go over the top or something like that. Okay, let's do it. Here's the theorem. And I also have to do this video in like 10 minutes. Here's the theorem. For a connected multigraph G, so first of all, I'm insisting the graph be connected. If it's disconnected, it's kind of pretty stupid, because then there are certainly no trails which use every edge exactly once, because if the graph is disconnected, I can't even do that. So let's concern ourselves only with connected graphs. And yeah, we do want it to be a multigraph. I mean, that's sort of in the spirit of the original problem. Notice that this bridge problem, when converted to graph theory, is a multigraph. Here's the claim. The claim is that this exact characterization of graphs, whether they are, well, people even say whether the graph is Eulerian. And the graph is Eulerian if there exists an Eulerian circuit. Some people say Euler circuit. Our textbook says Euler circuit. Some people say Eulerian circuit. It's harder to say. Anyway, well, it's a very simple property that characterizes these Eulerian graphs. Does every vertex have even degree? Okay, and once again, it's possible to just give like a 5-second proof of this. And the gist is, right, if every vertex, so let's first prove this direction, which is kind of the trivial direction. And the idea is that you have a bunch of vertices that get visited in this circuit. Now recall that there's this distinction between a circuit and a cycle. What is the distinction between a circuit and a cycle? Well, a cycle starts at a vertex. A cycle is closed, so it's a walk that begins at a vertex and ends back at that same vertex. But in a cycle, we never visit a vertex twice, except for the first and the last. But a circuit, we may, in fact, revisit vertices. And so you should be thinking, anytime someone says a circuit, this came up in class, you should be thinking like figure 8 kind of thing, right? I perhaps might start here at U and yet go, visiting a bunch of vertices, hit some vertex V, and then hit that vertex V again, and then end at U. That would be an example of a circuit. And so it's not true that the set of vertices that you visit is unique. What makes a circuit, what is the actual definition of a circuit? It's a closed trail. And what's a trail? A trail does not reuse edges. Okay. And so we have to imagine that we're going to use every edge only once, and we're going to use every edge. This is what it means to be an Euler circuit. But we might revisit vertices. Therefore, any picture you draw is going to be a little bit misleading, because you're sort of tempted to draw it like this, but then of course some of the vertices are being reused. So if you're okay with high levels of abstraction, then you can just say, let start somewhere. What is even? This is a picture from some of my argument, right? So let your circuit be this. Let your circuit start with vertex 1, then go to edge 1, then vertex 2, then edge 2, vertex 3, edge 3, etc. And then we're going to go all the way until we hit vertex VK, and then there'll be the final edge EK, and then back to V1 again. Okay, well, yeah, that is a circuit, but these vertices are not necessarily distinct, right? So I don't know, what do we say that? We could say that VI, not necessarily non-equal to VJ or something like that for I not equal to J. Okay, so if you're okay with that, then these vertices are not, the indices of these vertices are not indicating some absolute name of the vertex in the graph, but rather they are the labeling of the vertex of the order in which the vertices of the graph G are visited in the particular circuit. Okay, and what do we need to show? We need to show that every vertex has even degree. Okay, and I think that maybe just in the interest of time and not boring people, I'll just kind of give the fast version of this, right? The fast version of this is, look, if the graph is Eulerian, every edge is used exactly once. And every edge is used. Every edge is used at most once. That's what makes it a trail. But also, every edge is used. So if every edge is used in the circuit, then in fact, every edge appears in this exact specification of this circuit. Every edge appears exactly once. Every edge is, by definition of edge, incident with exactly two vertices. Okay. Then take an arbitrary edge in this sequence of vertices and edges, which defines the circuit. Well, every edge appears in this circuit flanked with precisely two vertices. And so, as I list each edge in this circuit, and there are always two vertices on the left and right of this edge, they are precisely the two vertices which are incident with this edge. Okay, and so, okay, good. But then, yeah, okay. So therefore, but okay, also, what is the degree of a vertex? The degree of a vertex is the number of edges incident with it. Okay, so if you sort of take some kind of arbitrary, vertex of your graph, and you ask, what is the degree of that vertex? It's just the number of edges which are incident with it. But also, every edge is going to appear somewhere in this circuit. And so you can also just say, this is a level of detail that no one goes into, that the degree of any vertex in the graph is the number of edges that are incident with it in this circuit, since in fact this circuit contains every edge. And therefore, maybe the better thing I should have circled is this kind of situation, right? Consider the appearance of any vertex in this sequence of vertices and edges which defines the circuit. It is always flanked by precisely two, any vertex except the first one is flanked by precisely two edges. And yeah, so that's two, right? And okay, so in other words, and recall that this particular vertex might appear multiple times in this sequence. But every time a vertex appears in this sequence, it appears flanked by precisely two edges. And so okay. So if you add up the total number of edges flanking any vertex in this circuit, then it's always a multiple of two. because every vertex in the interior of this sequence appears, however many times it appears, flanked by precisely two edges. So there we go. And every edge is being accounted for because it's Eulerian. And then, of course, I guess the final comment is the first and the last one, right? That the first vertex gets one edge over here, but then one edge over here as well. So okay, therefore, the total number of edges incident with any given vertex must be even. And if the total number of edges incident with any vertex in this circuit is even, and since this circuit contains every single edge, then the total number of edges incident with any vertex in the graph is even. And that's just another way of saying every vertex has even degree. All right, the 10-second proof of this is just, dude, you go around and every single time you go visit a vertex and then you leave again, then you reduce the degree of that vertex by 2, and so they always come in pairs. And so since we eventually hit every vertex, why do we eventually hit every vertex? Because every vertex has degree greater than 0. The graph is connected, and so we use every edge. Then they always come in pairs of 2. Okay, that was a little bit fine, but maybe not perfect. Okay, we push on. This is the much harder case. If G is a connected multigraph whose vertices all have even degree, then G contains an Eulerian circuit. All right, so I guess I'm just going to do this with my pen. Okay, here we go. I have here an arbitrary graph in which I'm going to prove this algorithm. And this is exactly taken from the book, but hopefully I'm going to do a better job actually explaining what's going on. So we have a connected multigraph, and now it's the converse of what we just showed. Now I start with an arbitrary graph, an arbitrary number of vertices, and an arbitrary number of edges. And all I know for sure is that it has the following property. All vertices have an even degree. And Euler proved this, I'm pretty sure he did, that if all the vertices have an even degree, there must exist an Eulerian circuit. And we say the graph is Eulerian. Okay, how do you do this? Well, first let us find the degree of every vertex. So this is 6. No, that's not true. This is 4, 6, 4, oh my gosh, 1, 2, 3, 4, 5, 6. Why did I make this example so hard? I'm not really sure. 4, V6 is 2, V7 is 4, V8, 4, V9, 4, V10, 1, 2, 6, V11, 4, and V12, 4. Okay, so I have to catch a train in like 20 minutes, so let's just do this really fast. What are we going to do? Here's the algorithm. It goes like this. Begin with an arbitrary vertex V1. So let's start with green. So I'm going to start at vertex V1. And here's what I'm going to do. I'm going to start here. And then I'm going to draw an arbitrary vertex. So here, to select an arbitrary edge. Okay, and now maintain somewhere on the bottom a running count of like already visited, all right, visited, yeah, vertices. I love Zoom School. I hate that my handwriting is so bad with this pen. It's so good with a real pen. Anyway, we push on. So what have we just done? We've just added this vertex. We've added this edge, this green edge. Okay. What does that do? Well, by adding this edge, I change the degree of vertex 1 by 1. And so the remaining degree, this is like this initial column is the actual degree of the vertex in the graph. What I'm going to do is I'm going to go through this algorithm. I'm going to prove to you that this algorithm does what it's supposed to do. And this algorithm is going to just construct an Eulerian circuit. Okay, so I have to prove to you that this algorithm, I have to explain the algorithm. I have to prove to you that the algorithm terminates. I have to prove to you that the algorithm does what it says it's going to do. Okay, so what is the algorithm? You pick an arbitrary vertex. I choose V1. Of course, the graph is connected. So that means that every vertex has some degree greater than 0. And therefore, there are edges coming out of that vertex. Select one at random. All right. Well, now we're at a new vertex, V8. And now, you're at vertex V8. Well, we used up a degree of V8 coming in via this green edge I just drew. And now we're going to use an edge coming out. And so now the algorithm says select, so I should say that the assumption of the problem is that all the vertices have even degree. So if all the vertices have even degree, then I use a degree coming in. So then there's always at least one more left coming out, right? That's the idea. This degree of V8 has to be at least 2. If the degree of V8 is at least 2, then I'm not going to get stuck ever leaving V8. So I use an edge coming in and an edge coming out. So what just happened is that the degree of V8 just got reduced by 2. And now I'm at vertex V9. Well, again, vertex V9 by assumption had even degree. So I used an edge coming in, and I'm going to use an edge coming out. And so now I choose an arbitrary edge from among the edges incident with V9. There must be one, because as there were an even number of edges, when the edge connecting V8 to V9 was added to the circuit, well, then the remaining degree of V9 became odd for a moment. And since the remaining degree of V9 was odd, then there's always another edge incident with V9 that hasn't been added yet to the list of already used edges. Okay, you could go even into more detail here. So what happened to V9? Well, it went down by 2. And now we're at V5. And similarly, V5 went down by 2. Always a degree in, always a degree out. Because the degree was even, it became odd when I went in and became even again when I leave. This is almost the whole proof. I could just practically stop now, but we just kind of keep on going. So V11, we lost 2. And V12 now, okay, so notice what keeps happening. Well, I'm pretending that this algorithm is completely arbitrary, so it requires no sort of foresight or thought or anything. I'm just picking vertices kind of randomly. So what can happen? Well, could we go on forever? No, because the graph is finite, so there are a finite number of edges. So at every step I use one edge, there are a finite number of edges, so no, the algorithm's not going to go forever. Could the algorithm get stuck? Well, the only way for it to get stuck would be if I entered a vertex that I could never leave from again. But of course, that's not going to happen because every vertex has even degree. And when I enter that vertex, I remove the degree by 1. And so there's always an odd number of edges left. Or in other words, the remaining degree, I'm inventing this thing called remaining degree, which I think is pretty self-explanatory. It's the degree of the vertex after removing the edges as I add those edges to the circuit. And so the remaining degree of every vertex as I enter that vertex, as I add that vertex to my circuit, the remaining degree is always odd, so there's always a way to leave. Okay, so what's going to happen if I can't get stuck and I can't go on forever? Then eventually I will have to go back to V1 again. Now, I don't know, that strikes me as maybe something, maybe that's kind of obvious, maybe that's kind of a little bit tricky. Why must I eventually hit V1 again? Well, I must eventually hit V1 again because, once again, the algorithm, it can't go on forever, but it also can't get stuck. And so what's the only thing that can happen is I have to eventually hit V1 again because V1 had an odd V1 itself, the arbitrary vertex on which I started this algorithm, had even degree. So since it had even degree, the remaining degree of V1, as I removed an edge, went down by 1. So the remaining degree of V1 is odd. And so V1 still has edges incident with it that have not yet been used. And therefore, a random walk that you construct by just picking an arbitrary vertex must eventually hit V1 again. Because the only alternative to not hitting V1 is to get stuck or go on or go on forever, and neither of those can happen. So as V1 still has edges left, we have to hit V1 eventually. Okay, and so what happened? V12 went down by 2. Did I do V11? Went down by 2. And V1 went down by 2. So the remaining degree of V1 is 2. Okay, so in other words, what have I constructed? I've just constructed a circuit. I've just constructed, by picking arbitrary vertices, and in fact, you could even have used a vertex twice in this circuit. In this case, I didn't, but you could have. I made a circuit. Is this an Eulerian circuit? No, because I didn't use it's a circuit in the sense that I didn't reuse edges, because built into the algorithm is that I sort of remove the edge. As I use it, I remove the edge from some updating set of edges yet to be used. And is it Eulerian? In this case, no, because there are edges left. Now, I might have, by accident or luck or whatever, used every single edge on round 1. But if not, I move on to round 2. Okay, how does round 2 work? In round 2, let me switch colors. In round 2, I just change the... So I now have this circuit, right? This green circuit is my round 1. Okay, well, the graph is connected. So every vertex in the graph, for every vertex in the graph, there's a walk from that vertex to V1, say. So if there's a walk from that vertex to V1, then there's also a walk from any vertex to all of the vertices. That's the definition of connected in this circuit. So of all the vertices, V1, V8, V9, V5, V11, V12, these are the already visited vertices. I was going to update this as I go, but I don't feel like it, right? I have this list of already visited vertices. And so the question is, or the claim now is that there must exist some vertices on this circuit with edges yet to be used. Why? Because there are, by assumption that the algorithm hasn't completed yet, edges left to be used. And if there are edges left to be used anywhere, there must be some edges left to be used among the vertices that have already been visited. Because if not, then if all the edges left to be used if none of the edges left to be used were incident with any of the vertices that we had already visited, then in fact there would just be no walks from the vertices that we'd already visited to the vertices yet to be visited. But we know that can't happen because the graph is connected. Therefore, I may pick some arbitrary, now I choose V12 because just why not? And maybe I should do this, right? This is V1. Let's put a thick dot on where I start the second, I'm going to miss my train, the second stage of the algorithm. And now, once again, I just start, right? And I just drew arbitrary, and I just kind of start drawing, man. Here, I go to V2 again, then maybe down to V4, then, whoa, I don't even know how am I going to get back again? I guess I need to get to V7, right? Yikes. So, I have to get to V1. So, okay, here we go. So down to V10, and then up to V1, and then to V7, and then back to V12. So what happened there? I started at V1. Its degree went down by 2, so its remaining degree is 0. I used 1. Oh, no, let's go in order. That is true, but what did I do? I don't even remember now. But maybe I went from V12 to V2. That's probably what I did. Oh, man, I don't even know. I forgot the order I went in. But I certainly used up 4 from the degree of V2, so that's 2 now. I used up 2 from the degree of V3. I used up 4 from the degree of V7. I used up 2 from the degree of V4. I used up 2 from the degree of V10. I used up, let's see, 10, 4, 3, 1, 2, 3, 4, 5, 6, 7. So what am I forgetting? Just V12 itself. And so this is now down to 0. Yeah. This should be, no, this should be a 4 here, right? Yeah, the remaining degree here is 4. Okay, on V10. Woo! Good. So now what? Well, now I have this sort of new situation, right, in which I started here at V1. I made a circuit, but now I made a new circuit by arbitrarily picking some vertex along the first circuit and choosing to go off on like a kind of like an extra loop. Okay, so but that's kind of fine, right? Because here was my original green circuit, and then I just picked a point on that green circuit and did a little one of these. So now you just splice this yellow one into the green one. So now you just say, okay, come on. You just go, you start wherever you wanted to start, say here, you go around, but now when you get to this point of V12, you sort of break off and you do this this yellow loop, and then you kind of do this last little bit again. So it's like this, and then. So you just splice in this little detour. Okay, I feel like we're just kind of done, but I want to be done with this video. What do I do now? I pick an arbitrary vertex from the yet to be visited vertices, and that might be, say V5. What am I going to do from V5? I'm going to go V6, V10, V11, V4, V9. No, I already, let's see, what else? I have to go now to V10. I have to go now to V2. And I have to go then, I think I'm going to be forced to finish this off right now, right? To V8, and then to V4, and then to V3, and then to V5. Okay, so what happened on that round? What happened on that round is everything just got reduced, man. V2 got visited. So that's now down to 0. V4 got visited twice on that circuit, so that's now down to 0. V5 got started and then ended there, so that's now that's also down to 2. V6 got visited, that's down to 0. V8 got visited, that's down to 2. And V9 down to 0. This is kind of boring. V10 got visited twice on that one. Yep, it did. Down to 0. And finally V11 also. Okay, and so this should be 0, of course. Okay, so here's the claim. The claim is this algorithm does the job, because of course then what did I do? I picked this point V5 and I spliced this in. Okay, so there are only a finite number of edges. At every stage in this algorithm, we used up a bunch of edges. And so the algorithm can't go on forever. At every stage of the algorithm, you pick an arbitrary vertex from among the list of already visited vertices, which still have unused edges incident with it. There must be some, because if the algorithm is not completed yet, there are still unused edges. And some of the unused edges might be edges connecting vertices that have not yet been used. But I think this is the subtle point. I'm not necessarily doing a better job than Gossett here. That if you consider at every stage the total number of unused edges, some of those unused edges must be edges that are incident with vertices that have already been visited at an earlier stage in the algorithm. Because if not, then all the edges remaining would have to be edges connecting vertices that are have not yet been visited. But if all the edges remaining connected vertices that have not yet been visited, then those vertices that had not yet been visited and the edges connecting them would be completely disconnected from the vertices that we had already visited, and we know that that's not possible because the graph is connected. Therefore, you may always select arbitrarily, as I did here, v1, v12, v5, a vertex from among those already visited, which still has edges incident with it that have not yet been used, and you may begin another arbitrary circuit. What does that circuit do? It starts and it just goes randomly around. Every time I visit a vertex, I am able to leave again and cannot get stuck because the degree of every vertex is 2. And in all previous stages of the algorithm, the degree of that vertex was reduced by 2. So the remaining degree of every vertex is also always even. So since I can't get stuck, and I can't go on forever because the number of edges is dropping, the only other alternative is that I return at each stage to the vertex that began that stage. And thus, by the time I finish that stage, I reduce the original vertex, in this case it was v1, v12, and v5, by 2, or by at least by by 2, exactly. 1 when I started, 1 when I ended. And then you just keep performing these stages until every single edge is used. And by splicing the stages together into one big circuit, we've created an Eulerian circuit that uses every edge exactly once. Okay, this video is pretty much over. I would just like to say, I think this is okay. There's one more sort of related concept, which is that of an Eulerian trail, which I mentioned already earlier. What's an Eulerian trail? It's just like an Eulerian circuit, but now we don't necessarily insist that it be closed. A circuit is a closed trail. So an Eulerian trail could start at one vertex and end at a different vertex. So now it's possible to have a degree, say, 1 vertex. But every other vertex, let's see, maybe just, this is like extremely boring, but something like this, right? So you start here and then you just go, and that would be an Eulerian trail. So what matters in an Eulerian trail is that the internal vertices have even degree, but the starting and ending vertex can have odd degree. And this is kind of just, again, sort of obvious. There is a kind of a cute little proof of this, though. This is also characterizes this completely. Suppose G has exactly 2 vertices of odd degree. So suppose there's this vertex v1 and there's this vertex v2, and these are the only ones with odd degree. So, just do something like this. And then there's this entire other graph where every other vertex has even degree. I would like to claim that G has an Eulerian trail. Well, all the heavy-duty work was done in the previous proof. So now I'm going to make this following sort of cute argument. Well, temporarily connect V1 and V2 with an edge that in fact does not exist in this graph, let's say. And actually, it's a multigraph. So even if V1 and V2 did have an edge between them, just add another one. Okay, by adding another edge between V1 and V2, I've now increased the degree of V1 by 1, and I've increased the degree of V2 by 1. And since these were the only 2 odd degree vertices, they are now even degree vertices. But also every other vertex in the graph was already even. That's the assumption here. Exactly 2 vertices of odd degree. So now I have a graph where every vertex has even degree. And now, by the previous theorem, there exists an Eulerian circuit. And this Eulerian circuit uses every edge exactly once. And if it uses every edge exactly once, in particular, it must use this V1, V2 edge. And so now, just remove the edge, right? Now, get back in there and take this out again. And whatever, and then just start at V1. So, basically, just remove one edge from your circuit, start at V1, then we just end at V2. Basically just like rotate the circuit in such a way because the circuit is ultimately sort of circular in a kind of a way. So so it can begin and end in anywhere, and now just follow the vertices of that circuit, but instead beginning at V1, it will just now end at V2. Okay, and then the converse is maybe a little bit trickier, right? This is basically now just repeating the entire argument. If there is an Eulerian trail, sorry, I should have said, but not an Eulerian circuit. So trail, but not an Eulerian circuit is also part of this here, right? Okay, and here again, there's an Eulerian trail, but not a circuit, then there are exactly two vertices of odd degree. This is now the converse. Why must that be true? Well, you just kind of repeat all the logic from the previous proof again, right? If there's an Eulerian trail, but not a circuit, then, well, if there's no circuit, then I think I'm just going to stop this video, right? Then okay, we'll take that circuit. It has a starting point and an ending point, and in fact, those starting points and ending points, if there's no circuit, but there is a trail that goes from V1 to V2 through a bunch of other vertices, then if there were an edge between V1 and V2, then there would be, if I were to add another edge between V1 and V2, there would be a circuit. So there must be no edge between V1 and V2, or sort of not enough edges or something like that. Then I have to show that there are exactly two vertices of odd degree. Well, it's just the same kind of thing, right? These two vertices must have odd degree because I start here at V1 and I end here at V2. As I leave V1 the first time, I reduce its degree by 1. And every internal vertex which is visited gets its degree changed by 2 each time, and then back to V2 as well, same thing. Okay, good, bye.